So here's problem 2 from the FRQ section of the BC Bluebook test preview. This is a parametrically based problem, very typical of what normally sits in the second calculator position. On the interval 0 to 5, we got a particle moving along the curve. Position at time t is given by x of t, y of t. So it's moving along a parametric curve. At time 1, the particle is at position 2, -7. And we know the velocity components in both the x and y direction, right? So they provide us with dx dt and dy dt. They ask us in part A to write an equation for the line tangent to the curve at the point 2, -7. So the main thing that I need to know here is what my slope of the tangent line is. And in parametrically based problems, we're going to find the slope of the tangent line by finding the instantaneous rate of change of y with respect to x at the location where we would like to determine it. We're going to find that by taking dy dt divided by dx dt. Now you do have to realize that you're not putting 2 and -7 anywhere. We are at this ordered pair at t equals 1. So we're needing to evaluate dy dt at 1, evaluating dx dt at 1. Calculator's in place. You can definitely do this with the calculator. You should end up with a slope of 6.938. I've got the point slope form version of the equation of the tangent line. You can do slope intercept if you wanted to solve this for y and kind of go to that intermediate form that you see a lot throughout your calculus course. That is all fine. Part B asks us to find the y-coordinate of the position of the particle at time 4. I know the y-coordinate is -7 at time 1. So what I'm going to do to find the y-coordinate at time 4 is I'm going to take the y position that I know, -7, and I'm going to add on how much the y-coordinate changes by from the time that I know it to the time that I want it by integrating the rate of change of y with respect to time. So this calculation is something that can be done with a calculator. I've got a little Desmos input here. So you literally just type this in, -7 plus, and if you literally type in int, it'll give you the integral symbol. You can fill in the rest, and you end up with -5.007 as that y coordinate at time 4. Part C asks us to find the total distance traveled by the particle on the interval from 1 to 4. So you're going to integrate speed on the integral 1 to 4 to find the total distance traveled across that interval. Or you can just call this the curve length formula. Both of those end up being the same calculation. So I show the integral that I need to do. Again, I can do this on Desmos. This is a little messy to type in. You do have to be really cautious of your grouping symbols, and that's with the Desmos input as well as the graphing calculator input if you were going that route. But what you should end up with here is 2.469. Last part of this, find the time at which the speed of the particle is 2.5. So I've got my calculation for speed, right? Basically the magnitude of the velocity vector. I haven't plugged in any specific time. I want to know a time when my speed is a certain value. So I show I'm setting my speed equal to 2.5. I can go to a graphing calculator. I've got Desmos going on here. So I've got my speed graph showing up in red. I've got my y equals 2.5 graph coming across in blue. I went ahead and clicked, and I have my intersection between those two having a t-value of 0.41501. There is a secondary part to this. When I first recorded this video, I had not done the secondary part. Find the acceleration vector of the particle at this time. So I've got that happening here. The acceleration at that time is going to be the second derivative of x evaluated at that spot, comma, the second derivative of y evaluated at that spot. I have Desmos input here. It's a little clunky to use Desmos to do this just because you can't really type in dx dt or x prime of t or anything like that, just due to some of the things that Desmos is recognizing as derivatives. So I just kind of called the x component of velocity v of t, the y component of velocity w of t, and then I found v prime and w prime, my x and y components of acceleration.